So we're learning about derivatives and how to think of a derivative as a rate of change. And if you think about the way velocity changes, we call acceleration. So when you get to the top of that second page for your 3.4 notes, acceleration is the first derivative of velocity. But wait a minute, velocity was the derivative of position. So that means this is our first example in real life of a second derivative. Velocity is the derivative of position, and acceleration is the derivative of velocity. So we say acceleration is the second derivative of position. And you can see the two different notations you might use for derivative to say that. So these go at the top of your back page of your 3.4 notes. So I have an example here. If I know the position of a particle moving along a straight line is given by this function, s of t is t squared plus 4t plus 4. I'm going to find the acceleration of the particle at time t equals 4. Well, as of now, as of section 3.4, you now know how to find acceleration given position. You need to find the second derivative of position. So that's what we're going to need to do. We're going to find an expression, a function for a of t, acceleration. We're going to use that to find a of 4. So you can see my work here. V of t is s prime of t. I'm going to find that using the sum and difference rule and also the power rule, so the 2 comes down to the front. So first I have to start by finding v of t. Once I find v of t, I can find v prime of t, which is another name for acceleration. So acceleration is going to be the derivative of v, or the second derivative of position. The derivative of 2t plus 4 is 2. Well, that's interesting. It turns out that this acceleration function doesn't actually depend on time. It's always, there's a constant acceleration of 2. So a of 4 is equal to a of anything, and a of anything, we've just found out, is 2. Sometimes you might get asked a question like this, and you would have to find acceleration, and you would find that acceleration is a function of time, in which case that input value is going to change the output value. In this case, it didn't happen to. All right, so just some things to think about here. We're starting to translate between graphs and like a word understanding of what's happening. And now that we know that there's a function position, its derivative is velocity, and the derivative of velocity, or second derivative of position, is called acceleration. So we're going to spend a lot more time on this in chapter 4, but watch what you can see. If this is my position function, so that means we're graphing distance here, check this out. At this part of the graph, the distance is increasing. That means the slope of the distance is positive, which means velocity must be positive. Then I want to ask myself, is the slope positive and getting steeper, or is it positive and getting flatter? Here, it's sort of, so here, there we go, sorry, I got cut off there. The slope is flatter here and getting steeper. That tells me that the velocity is increasing, which tells me the derivative of velocity, acceleration, must be positive. Here, the slope is positive, so velocity, the slope, this is the distance graph. The slope is positive, so velocity must be positive. But the slope is not changing, so the velocity is not changing. That means acceleration is 0. Here, I still have increasing position, which means my velocity is positive. Remember, which means motion must be forward, whatever forward means in this context. But now I had steeper parts here and now flatter parts here. That means the velocity is still increasing, but it's not the velocity is still positive, but it's not increasing. That tells me the velocity is decreasing, which means the acceleration is negative. So here's the cool thing. That's just practice. Like I said, we're going to talk about that a lot in chapter 4. So anything about that you can understand now is just kind of bonus. We talked about position and acceleration and velocity. We can still talk about the rate of change of a function. It doesn't have to be that the input is time. There are other ways that functions change. They don't always change according to time. So Let's look at this example from your handout. If I have the area of a circle, how the area of a circle changes depends on the radius. So I can take the derivative of this area function with respect to the radius. So I imagine that the radius is the input variable. It's actually the only variable here, right? The 2 can come to the front, and I get the derivative of the area with respect to the radius is 2 times pi times the radius. So, instantaneous rate of change. What is the rate of the change? Oh, so that's where this picture came from. There we go. So think about a tree trunk, right? The area of that cross-section changes depending on how big the radius of the tree trunk is. That's the cool thing about calculus. We didn't used to be able to talk about how functions change. So now we can answer this question. The rate of change of the area when the radius is 4 feet. So that's going to be dA dr, which I already found, but with the r replaced by 4. So this notation for the derivative, it doesn't have parentheses that you can plug a number into. So if we want to evaluate that at a certain value, we put this vertical bar here, and we say what value we're plugging in for r. So this is 2 pi r with the r replaced by 4, and that gives me 8 pi. More about the units and how we're going to use those coming up later in chapter 4.